brief idea about the four fundamental theorems of norm and Banach spaces, namely Hahn-Banach theorem, uniform boundedness theorem, cross graph theorem, and open mapping theorem, and related concepts which will be used in further study of these theorems. Today we will discuss the Hahn-Banach theorem. It is basically an extension theorem for a linear functions. So, Hahn-Banach theorem, it is an extension theorem of linear functionals. Now, this theorem gives a guarantee that there are adequate number of linear functional on the norm space, or norm space are enriched with the bounded linear functional. Hence, the theory of the dual space can be taken up very well and gives you the results which we need for that. Now, normally this extension problem is basically, we mean by an extension problem, say suppose Z is a subset of X and an object which is defined on Z, we wanted to extend this object on the entire X in such a way that the basic property of this object remains intact. Then this problem is known as the extension problem. In case of the Hahn-Banach theorem, the extension problem is our linear functional. So, where we have the linear functional defined on a subspace Z of a vector space X, which satisfy the certain property of boundedness, that is, which is dominated by a certain function p x, which we will define later on as a sublinear function and so on. Now, this linear function which is measured by a certain function p x, we wanted to extend it to the entire vector space such that the property of the linearity and majorization remains intact. So, this is what we do in case of the Hahn-Banach theorem. So, basically we say in Hahn-Banach theorem, the object to be extended is a linear functionals f which is defined on a subspace Z of a vector space X and has a certain boundedness property. Now, this boundedness property we will take up in terms of a sublinear functional. Okay. So, we will use the first taking as a definition of the sublinear in terms of the sublinear functional. In terms of sublinear functionals. Okay. Sublinear functional. What is the sublinear functional? Let us first introduce the sublinear functional. Okay. A sublinear functional Px is a real valued functional is a real valued functional on a vector space X which is subadditive that is P of x plus y is less than equal to P x plus P y for all x comma y belongs to capital X and positive homogeneous that is the meaning is that P of alpha x equal to alpha times P x when alpha is for all alpha greater than equal to 0 in R and x is an elements of x and for x belongs to capital X. So, such a functional P which is subadditive and positive homogeneous is said to be a sublinear functional. Okay. Now, we wanted this functional f to be extended from z to x which satisfy the property that f is linear functional and dominated by or majorized by the function p, that is f x is less than equal to p x for all x belonging to z. Okay. Then the Hahn-Banach theorem says that we can extend this functional f to the entire x such that the extended functional f retains the property of linearity as well as majorization. So, this is the crux of the theorem. Okay. So, we will see the exact statement of the Hahn-Banach theorem is this is first we will do it for a vector space, for real vector space. In fact, the Hahn-Banach theorem is first introduced by Hahn in 1927 and then later on in a modified form by Banach in 1929. So, this is discovered, it is discovered. So, I think it's the Hahn-Banach theorem, it is discovered by H. Hahn in 1927 and in a modified form by S. Banach in 1929 in the form by Banach in 1925. In that, then this Hahn-Banach theorem it discovered real for the real S for real vector space, and later on it is extended to complex vector space by H.F. Hahn Blust and Sovek Jaik in 1938. Okay. So, we will discuss this Hahn-Banach theorem first for the real vector space which is discovered by Hahn and Banach, That is why it is called the Hahn-Banach theorem. Okay. The statement of the Hahn-Banach theorem is, let X be a real vector space. Let X be a real vector space. X be a real vector and P a sublinear functional on X. Further, let F be a linear functional. Let F be a linear functional which is defined on a subspace Z of X. Z of X and satisfies the majorization property, satisfies f x is less than equal to p x. Now, let it be, this is one, this property we will use as second, and this one is third for all x belonging to Z. For all x belonging to Z, this is third. Okay. Then what this theorem says, then f has a linear extension say f delta from Z to X, satisfying the property f delta x is less than equal to p x for all x belonging to capital X. Let it be 3 star, that is f delta is a, that is f delta is a linear functional on X and satisfies 3 star on X, and f delta x equal to f x when x belongs to Z, for every x belonging to Z. So, it is an extension for them. Okay? Clear? So, this is a statement for the real. Now, we will prove this theorem in 3 steps. In the first step, we will consider a class E of the set of all functional f which are the extension of f, that is set of all linear extension of f on E, satisfying the condition of majorization. And then we will see that a suitable partial order can be introduced, which will convert this set E into a partially ordered set. Then by applying the Ron's lemma, we can get a maximal elements, and that maximal element we will see that it behaves as our desired function, that is it will be linear on the entire x and majorized by p x. So, in the second step we will prove that this f delta which you are getting is a desired function on the entire space x, and in between establishing this we need certain auxiliary relation. So, that will we will show in the last step that is step 3. So, the proof of this will be divided into 3 steps. Step 1, what we do in that, the set E of all linear extensions G of f, linear extension G of f, satisfying the condition g x is less than equal to p x on their domain d g can be partially ordered. And Jones lemma yields a maximal elements f delta of f. Okay. Then second step, what we do is f delta so obtained is defined on the entire space X. And third step, we will use an auxiliary relation. Which is used in part B, which is used in step 2. Okay. So, the proof of this we will break up into 3 steps. In the first step, we will show the existence of f delta, and second step we will show this f delta in fact is the entire defined on the entire X, and third step a relation will be proved which is used for establishing the step 2. Okay. So, let us see the first proof of the step 1. So, suppose E be the set of, let E be the set of all linear extensions G of f. F is already given to a linear functional defined on Z, which satisfy the condition g x is less than equal to p x for all x belong to the domain of G, for all x belongs to the domain of G. Okay. Now, this E is clearly a non-empty set. Why? Because f belongs to E. Why? Because f is linear and majorized by this okay, in the domain of f, where x belongs to the domain of f. So, it is a majorized by this and x belongs to this domain. So, there exists at least one element f belongs to E. So, E cannot be, E is different from empty set, sorry, E is different from, E cannot be an empty set. Okay. So, we can now introduce the partial order on E. on E, we define a partial ordering as follows. G is rated to H if H is an extension of G, where G and H are belongs to E. E is the collection of linear functionals. We are taking the two elements of E, that is two linear functional. We say that G is rated to H if H is an extension of G. That is the meaning of this, that H domain of H should cover the domain of G because it is an extension, and whenever the x is belonging to the domain of G, then H x must be equal to G x for all x, for every x belonging to the domain of G. Then we say H is an extension of G. Okay. Now, we claim that this is a partially ordering relation. Why? First is it is a reflexive. Each G is rated to itself, because G is the extension of G itself. Domain of G is covers G, its domain of G covers, and this condition is satisfied. So, it is reflexive property is satisfied. Antisymmetric. If G is rated to H, then this condition holds. If H is rated to G, then reverse condition holds, that is DG covers DJ and both. So, in fact both will be equal. So, domain of G and domain of H will be equal and they will satisfy. So, again antisymmetric and transitive also follow. So, it is a partially ordered set, that is we are able to introduce the partial ordering relation on E. Okay. Now, let us consider a chain in E. So, for any chain C in E, chain means a totally ordered set. Totally ordered set means that any two element of this class C are comparable. If we pick up any two element, either one is the extension of the other or vice versa. So, let us take any chain for this. Okay. Now, we define a new function G hat as by on this chain G hat, define G hat by G hat, define G hat which belongs to C. Okay, by G hat x equal to G x whenever G hat x equal to G x. Okay, if x belongs to domain of G, that is, in this chain I am defining the any arbitrary element G dash x you pick up, then it will coincide with one of the G x if x belongs to the domain of G. Okay. So, whenever the G dash x belongs to it, then it is chain. Okay. Now, this G dash clearly a linear functional. Clearly, G dash is a linear functional. Why it is linear? Because if I take G dash alpha x plus beta y, okay, then say alpha x plus beta y, then by definition this will be equal to G of alpha x plus beta y for if this point alpha x plus beta y belongs to the domain of G. is it not? Because it is a vector space. So, if x y belongs to it, then the domain, and G is a linear. So, it will be taken as G of this G of y, because G is linear. G is linear. Okay. So, we get this thing, that is G dash is a linear functional. Okay. The domain of G and the domain of G head will be the union of all the domain of G where the G belongs to C. Because when you take the x, then x may belongs to the domain of G1, x may belongs to the domain of G2, like this. So, for all G dash x is defined as G1 x, G2 x, and so on, depending on x. So, domain of G dash will be the union of all the domains of the G hat. Okay, the G belongs to C. Okay, where G is a element or linear functional in C. Now, obviously, this is a domain of G head is a vector space. Why? Because domain of G, it is a vector space. G is a linear functional defined on a vector space, and this is a chain, because C is a chain. That is why we can get the unions of this will be a domain. Okay, is a vector space. Now, another point which we claim that G hat in fact is a maximal element of C. We claim G hat is an upper bound of C, is an upper bound of C. Why? Because like this, if we take x is any elements of this, because if suppose x I take in the domain of G1 intersection domain of G2, then what happens is that with G1 and G2 belongs to the chain C, then according to this G of x1 equal to G of x2, because it is a common element, and since C is a chain, so this G1 and G2, G1 G2, this is not x2, G1 x equal to, since C is a chain, so they are comparable. So, either G1 will be less than equal to G0. So, either G1 is less than equal to G2 or G2 will be less than equal to G1. One of them will hold, but always G will remain, that is less than equal to G hat, because G hat will be according to this G hat defined as G x if x belongs to G. So, G hat will be G1 x or G hat will be G2 x. Therefore, in all the case G hat will be the upper bound for this. So, this shows the G hat will be, this is true for all G belongs to C. Therefore, G hat is an upper bound of C. Okay. So, this will be, now E we have already established is a partially ordered set, and C is a chain. Every chain, C is an arbitrary chain. Now, every chain has an upper bound. So, according to the Jones lemma, it must have its maximal elements, because Jones lemma. So, we say since C is a chain, in which C has a, which has an upper bound, and C is an arbitrary chain of E. So, if you take any arbitrary chain C, it will have a upper, that is every chain, every totally ordered set in E has an upper bound. So, by John's lemma, E has a maximal element. Maximal elements, maximal element f delta, say f delta, okay, say f delta. So, what do you mean by this maximal element? It means by definition. So, by the definition of E, E is the collection of all the linear functional, and f delta is an element maximum. So, it will also be linear functional, okay, and majorized by P. So, by the definition of E, this is this means that is f delta is a linear extension of f which satisfies the property that f delta x is less than equal to p x for x belonging to the domain of f delta, and let it be 4. Okay. So, we have established the existence of f delta. Now, we will show that this f delta is linear on the entire x, defined on the entire x. So, step 2. Okay. We now show that, so if it is defined on the entire x, it means the domain of d f bar, if it is x, then we say it is defined on the entire x. Okay. So, we now show to prove the domain of f delta is the entire x, okay, is all of x. Suppose this is not true. Suppose d of f delta is not equal to x, that is there exists some point x1 x which is in x, but not in real. So, there exists. So, we can choose a y1, a point y1 in x minus domain of f, x minus domain, that is x, or we can also write that is equivalent to x difference domain of f delta, okay. Consider which is in x, but not in. Now, consider a subspace y1 of x, x spanned by the domain of f delta and by 1. Okay. Domain of delta, that is any element of this by 1 can be expressed as the sum of the elements of the df bar plus the element alpha of by 1 type. So, that is one can write. So, any x belonging to y1 can be written as x is equal to y plus alpha by 1, where the y is an element in the domain of a. Now, one more thing which I want. Now, here when we say this y1 belongs, clearly this y1 is not equal to 0. Why it is not equal to 0? Because the domain df val contains 0 and by 1 is a point which is not in domain df val, because 0 is an element belonging to the domain. Domain of A is a vector space and it contains 0 element. So, by 1 will be different from 0. Okay. So, let us take the subspace which is generated by the df val and by 1, that is by the spanning of dn val and the alpha by 1. Okay. This one. Now, we claim that this representation that is unique. First, we claim that this representation is unique. That is, if we take suppose two representation, suppose that is if x can be written as by plus alpha by 1 and same as say by bar plus beta by 1, where by and by bar these are the element of the domain f bar and alpha beta are scalar, then this implies that by minus by bar is beta minus alpha by 1, but left hand side by minus by bar is a point in domain f bar and right hand side y 1 is not a point in domain of f bar, sorry, is not a point in, yes, it is not a point in because it is in outside of y domain of f bar, but 0 is there. So, the only this result holds. So, only possibility is that this by minus by bar should be 0, that is by is equal to by bar. So, the representation is unique. Okay? This shows representation unique. Now, once we have this representation, let us introduce the linear functional. So, introduce a functional G1 on by 1 as follows. We are defining the G1 on by 1 means the element will be of the form by plus alpha by 1, where y is in DFR and by 1 is a point not in DFR, as the f delta by plus alpha into C, where the by belongs to domain of f bar, okay, and C is a real number. C is real number. Then clearly G1 is linear, because if I take by, because if I take the y1 say alpha, let it be some like this, by is replaced by say replaced by y, a by dash by 1 by dash plus b by double dash, okay, and then pick up the two element like this. Then we say because of the f bar, because f bar is linear, therefore, it will break up into this and get the linearity. Okay. So, G1 is linear. So, I need not to show this part. Okay. See, G is linear. Then further, because alpha equal to 0, for alpha equal to 0, G1 by coincide with f delta by. It means G1 is a, that is, this implies that G1 is a proper extension of A, is a proper extension of f delta, that is an extension such that, that is an extension such that d f bar f delta, sorry, is a proper subset of is a proper subset of dg1 dg1 dg1. Okay. So, this is our domain of f delta, and here it is domain of g1. We say it is a, we have seen that this is a proper subset of this. Now, if I prove and g1, if I prove that g1 belongs to E by showing, okay. So, we if we prove that this g1, that g1x is dominated by px for all x belonging to domain of G, for all x belonging to the domain of G1, then this will show, this implies that G1 is in E, because it is an extension, okay? It is an extension dominated by P by C. Hence will contradict the maximality contradicts the maximality of f delta, because if f delta is maximum element, then a functional which is linear and extension of this cannot be an element of E. Here we have shown that G1 is an extension of f delta. If I prove that G1 also satisfies this condition, then G1 is linear dominated by P, measured with Px, then obviously the G1 will be the elements in E, hence it will contradict the maximality of f delta. So, this contradiction is reached because our long assumption that df delta is different from x. Okay. The contradict the maximality of f delta, hence so that df delta is equal to x, and that is what we wanted to show, that is so that df delta is x, means contradiction. So, contradiction of, so that df delta cannot be x. So, df, our assumption that df delta is subset of x is not equal to x is wrong. That is, df delta will be equal to x, hence this is true. Hence, it will give the f delta is a entire defined on the entire x. So, basically we wanted to this part, we wanted to show basically this portion. Okay. This is our, and this we will prove in the step 3. Okay. So, once it is established, automatically this gives you the proof of the Hahn-Banach theorem. Okay. So, let us see the third part. Okay. So, let it be this equation is 6, I think this 5, which one is 5 equation, G alpha, yeah, this equation let it be 5, this part is the 5th equation, okay, and let it be this is 6th equation. So, we will make use of the number, that is why we are putting that. Okay. So, now let us prove that G1x is less than equal to Px. So, what we do is consider the for any by n z. So, consider two elements, say by n z in d f delta, domain of f delta. Okay. Then start with this f delta z minus f delta y, or f delta y minus f delta z, because f delta is a linear, f delta is linear. So, by property of linearity, this can be written f delta by minus z, and then because f delta is dominated by the sublinear functional p. So, it can be written as this because this is the dominated by p, dominated by the f delta, this is by property, by assumption, okay, that is given in that, dominated by this. Now, this side we can write it as p by minus by 1 by plus by 1 minus by 1 minus z, and this will be because p is a sublinear functional. So, we can get the less than equal to p by plus by 1 and then p minus by 1 minus z. Okay. Now, transfer this to over there. So, what we get really is minus p minus by 1 minus z minus f delta z is less than equal to p of by plus by 1 minus f delta by minus f delta by. Okay. Now, by 1 is fixed element, okay, where the y 1 is fixed, by and z, these are the elements of d f delta. Now, left hand side is independent of by, right hand side is dependent on independent of z. So, if I take the supremum value of this side over z and the infimum value of y over y, then the result will continue to hold good. So, we take the supremum of this side, supremum of this side, left hand side, okay, left hand side is less than equal to infimum of the right hand side, where supremum is taken over z, infimum is taken over y. So, supremum and infimum both are there. Okay. Suppose these values are m naught and this is say m 1. So, there exists a real number c. So, for OSC, so there exists some c such that c lies between m naught and m 1, okay, which may be equal to also there. Clear? Therefore, this side 7, this will be 7th equation. Okay. So, this 7, so we get from 7, we get from here that minus p minus by 1 minus z minus f delta z is less than equal to c, and c is less than equal to p by plus by 1 minus f delta of y. Okay. This is true for all z belongs to d bar, d f bar, and this is true for all y belongs to d f bar. Clear? Now, let it be this 8a and this is 8b. Okay. This one is 8a, this 8b. Okay. Now, we wanted to establish 6. We wanted to establish this result 6. G1x is less than equal to Px for this. Okay. Now, G1x is defined by 5 as this fellow, x is by plus alpha by 1. So, this is x equal to this. So, we wanted to show 6. So, to prove 6, that is G1x is less than equal to Px for all x belonging to dg bar. All x we can write it as our alpha, that is x we can use it this one, that is G1 x means according to fifth by plus alpha by 1. This is okay. This will be the x is less than equal to Px. This we can put it for all x, this is it not, for x this is dominant. So, we want, in order to prove this thing, we will take the help of alpha, because alpha depends on it. So, to prove this result, we take alpha positive and negative both. Be proved, rather than be proved, when alpha is taken as positive, alpha is taken negative, or 0. Okay. So, our proving of 6 depends on alpha. So, we will choose first alpha to be positive, alpha to be negative, and alpha equal to 0. Then this result holds good. So, let us take this. First, alpha is positive or negative. So, choose alpha to be negative. Okay. Take alpha to be negative in 5. Then for in 5, what is the alpha is negative in 5? In 5, 5 means this. Okay. So, we wanted to prove this result when alpha is negative. Okay. So, positive let us replace z by alpha inverse y in 8a when alpha is negative. Okay. So, we get from here 8a, 8a is this problem here, this is 8a. So, here we can replace z by this. So, what we get is minus p minus by 1 minus 1 by alpha y minus f delta 1 by alpha y is less than equal to c. Okay. Now, multiply by minus by minus alpha, which is positive, this gives alpha of p minus by 1 minus 1 by alpha y plus f delta y is less than equal to minus alpha c, or this will be equal to what? Alpha, this is cancels. So, p of alpha minus alpha by 1 minus by plus is less than equal to f delta y plus alpha c, and this will be equal to x. Let it be put it x. So, this is equal to what? P x, is it not? So, P x, this is P x, and this one will be equal to what? F delta plus alpha is nothing but minus. So, what you are getting is, sorry, this is greater than, this will be transfer here. So, it is greater than equal to, greater than equal to this side, minus alpha is outside, and we are getting to be minus alpha p, yes, minus alpha is outside, then we are getting minus alpha into this, multiplying by this minus alpha. So, here also is minus alpha times of this. Okay. So, alpha, and then transferring towards this side, we get the minus, and this one will be equal to what? G1x, this is greater than equal to, what we are getting is here is p alpha y1 plus y, but this p alpha y1 plus y is our p x. So, we get G1x is less than equal to 0. Okay. Now, for alpha equal to 0, the result is obvious, and for alpha to be positive, in a similar way we can show that G1x is less than equal to f delta by plus alpha c, which is less than equal to p x. Hence, proof. This we can do. Okay. Thank you. Thanks.